In this video, we're going to consider the topics needed for section 3.1 related to eigenvalues and eigenvectors. Okay, the key formula in this section is the formula AV is equal to lambda V. Okay, the matrix A here, the matrix A will be given in the problem. Okay, this is essentially the matrix of your differential equation, or the right-hand side of the differential equation dy dt is equal to ay. Okay, so in this section, we need to consider how to find the straight line solutions of the differential equation, and the eigenvalues, eigenvectors are the important quantities. So here's just an example to kind of illustrate and get across the idea of eigenvalues and eigenvectors. And the question is this: is lambda is equal to -3 an eigenvalue of the matrix A, and that matrix is -1, 4, 6, 9. Okay, so that's the question before us. The key to this is to just think about the alternate way, or from the definition, that is, from the definition, what is being asked here. From the definition, we're essentially saying, is there a solution? Is there a non-zero solution to the equation AV is equal to -3V? Okay, a non-zero solution for V, where V is a vector. We'll say it's a two-dimensional vector of the appropriate size. We'll call it x and y. So A here is -1, 4, 6, 9. And V is equal to xy. We're hoping to find this, -3 times xy. If there's a solution to this equation, non-zero solution, then -3 is an eigenvalue of the matrix. Okay, so consider what this matrix equation, this is an example of a matrix equation. What is being asked here? One can use matrix vector multiplication to turn this into -x plus 4y. The first entry of the vector, 6, 9 times xy to get 6x plus 9y. And the question is that equal to -3x, -3y? Is there a solution for some x and y? Okay. Well, you continue to work this out, and you get yourself into solving a system of equations. Which can be solved in a variety of ways. First, maybe collect the x's and y's on a side by themselves, right? And therefore, that 6x plus 12y is equal to 0. Okay, so I've just converted this system and got the x's and y's on a side by themselves. Now, a variety of ways you can do this. I'd like to think about maybe multiplying the first equation by -3, which would lead to a new equation, -6x minus 12y is equal to 0, which, let's see, leads us into the direction of adding those equations together to give, very interesting, something, and we're going to add those equations together. 0x plus 0y is equal to 0. Okay, so what is the conclusion from this? Right, there's always something weird that happens in these eigenvalue eigenvector equations, and here we are asking ourselves what to make of this equation. So the easy way is to say, well, 0 is equal to 0, and you would say check. But another way to look at this is another way of saying 0 times x plus 0 times y, does that equal to 0? And you can say, yes, that's true for any x and any y. Okay, so let's look and see what happens here. right? Since 0x times 0y is equal to 0, you can say, okay, well, let x be anything you want. So x can be x, otherwise known as anything. Okay? And if x is anything, then put this into the other equation. 6 times anything plus 12y equals 0, and solve for the other value. Right? So y is equal to negative 1/2 of x. Okay? Since x could have been anything, y comes out to be minus 1/2 of anything. Okay? So I think what we've walked ourselves into, right, is that the solution to the original matrix equation here, the AV is equal to lambda V, that x could have been anything and y was negative 1/2 of that same thing. Okay? Which is another way of writing, factoring out the x, 1 negative 1/2. Okay. What does this say? This says that v, which implies that v can be any number x times the vector 1 negative 1/2. Notice that this vector is not equal to the 0 vector. So 1 negative 1/2 and any multiple of it should be an eigenvector of the original matrix. Okay. So let's take a step back and let's double check. Okay. So we were saying for the matrix, let's add another page here. 1 negative 1/2, add page below. Okay. So what we concluded that for the eigenvalue lambda is equal to negative 3, or for the value lambda is equal to negative 3, AV equals lambda V had a solution, a non-zero solution of V was equal to any number multiplied by, what was the answer down there? Sorry, 1 negative 1/2. 1 negative 1/2. Okay. And that was implied that lambda equals negative 3 was an eigenvalue, or is, I should say, is an eigenvalue of the matrix A is equal to negative 1, 6, 4, 9. You should definitely double check some things that are going on here. Check an example. Let's say that your number is equal to 1. Therefore, your vector v will be 1 negative 1/2. The question is, you should check, does AV is equal to negative 3v? Right? Is this true? Negative 1, 6, 4, 9. If you take that and multiply it by 1 negative 1/2, is that equal to negative 3 times that same vector? Okay, so here's the same vector in both places. Same vector. Or the self vector is on both sides. Okay, so multiply this out. Okay, negative 1, 4 times 1 negative 1/2, that would be negative 1, and then 4 times negative 1/2 is negative 2. Okay. 6, 9 times 1 negative 1/2 would be 6 minus 9/2, which is otherwise known as negative 3. 6 is the same thing as 12/2, so that's 3/2. Okay. And that's what you get from the left-hand side of the computation. Okay. If you check the right-hand side of the computation, say right here, the right side of the computation would be negative 3, 3/2 when you multiply. And those are, in fact, equal to the same thing. Okay. which implied that the vector 1, -1/2 was an eigenvector. Okay, that was the non-zero solution to the AV equal lambda V equation. Okay, so you can conclude by saying lambda equals -3 is an eigenvalue of the matrix, and then you can tack on to that, you can also add the fact that lambda equals -3 is an eigenvalue with, and one of the eigenvectors with eigenvector 1, -1/2. Okay. This is not the only eigenvector. Any number times that vector is also an eigenvector. So for example, the number, if you don't like the fraction there, the number could be 2, in which case another eigenvector would be 2, -1. Or the number could be -2, in which case another eigenvector could be -2, 1. Right? All of these are examples of eigenvectors. So the eigenvector is not a unique quantity. Okay? So what is typically said, right? A little bit of terminology here, is that the lambda equals -3 eigenspace is all scalar multiples of, and pick one of your favorite eigenvectors. So I like 1, -1/2 because that's the one we found by factoring. Okay? So the eigenspace is all multiples of 1, -1/2. And therefore you can say that your eigenspace, or your straight line solution, essentially is any number times 1, and then here's 1, -1, -1, -1, 1, 1 in all directions. So 1, -1/2. There is your eigenvector, 1, -1/2. But any multiple of that vector is the pink straight line here. So this straight line is the eigenspace for the eigenvalue -3. Okay? So that's an introduction to determining if a value is an eigenvalue of a matrix, and it all revolves around the equation AV is equal to lambda V.